So Earth Care is and still remains focused on shedding some more light between this nasty triangle here. It's the coupling between clouds, radiation, and aerosols and dynamics in the atmosphere. And where it begins and where it ends, it's hard to say because it is a cycle. So clouds are very diagnostic of the state of the atmosphere. If you have a cloud, it means there's a certain temperature and relative humidity there in probably aerosol environment. And clouds obviously affect the structure of the atmosphere. They reflect solar radiation and trap thermal radiation. And that affects the heating rate of the atmosphere, which changes the circulation. And then introduces the clouds help drive the winds help and define where the clouds are, etc. So that's why it remains let's say an essential area. After decades of hard work, still remains a challenging area when it comes to both weather meteorological models, so short-term weather prediction, and arguably the more important aspects of long-range climate forecasts. It still remains, pinning this down, remains, let's say, one of the largest sources of legitimate sources of uncertainty in our ability to predict future climate. And the more we learn about it, the more we learn about it, we think it's a tractable problem, but still, it's going to take better observations are certainly, and better modeling are certainly part of the solution. So in Earth Care has 4 instruments, and its idea not only, we focused on this, let's say you can think of this triangle as a bit of synergy, everything interacting. Earth Care itself is sort of like its own interacting system. So we have 4 instruments, a advanced cloud aerosol lidar, so it's a high spectral resolution lidar. So I'll explain what that means in another couple of slides. So it is an advancement over backscatter lidars like Calypso. There's also a cloud profiling Doppler radar, like CloudSat, but it has a Doppler capability, so we can measure fall speeds. And it is a little bit somewhat more sensitive than CloudSat. There's also a multispectral cloud aerosol imager, so you have the 2D, so the LiDAR and radar give you the horizontal context, the vertical context rather, and the multispectral imager gives you the 2D view like that. And there's strategies to put them both together. And on top of all this, you have a 3-view broadband radiometer, and that gives you the, okay, I'm explaining things to radiometer that's measuring both the total reflectance from the Earth at the total shortwave albedo, and then you have a long wave channel, and you have 3 views because you can't really measure a flux from space, but you get a much better idea if you measure the radiance at 3 different angles. And the idea is to put this all together, and it's kind of like and then that gives you the ability to do kind of an online closure experiment. So the LiDAR and radar give you the best vertical profiles of, let's say, the cloud and aerosol properties along the nadar. With the help of the multispectral imager, you can expand those retrievals out to a certain footprint on the order of 10-20 kilometers. Then you can do radiative transfer on that retrieved structure. And then you can actually calculate what, let's say, the broadband radiometer should be seeing. And if they match, that means your retrievals are self-consistent and you probably understand what's going on in that section of atmosphere. If they don't match, well, it could be something wrong. It could be a trivial software bug in the system. But if you, let's say, after we have enough measurements of different conditions, The actual science will be tracking down the circumstances in which we cannot get radiative closure. So if the retrievals are saying one thing and then our broadband radiometer says, no, you're missing something here, then that points to fundamental things such as we're not using, let's say, the right ice crystal models in scattering. The properties we're assigning to the aerosols aren't right radiatively. The surface temperatures are off, or etc. So that's one thing. So at the end, when everything gets up and running, we should be able to deliver to the scientific community products that are at least have this self-consistency check, which is a step above what most satellite missions can do. So even if we did not have collaborative measurements, which by the way are extremely valuable, we still could do the self-consistency check. And I can, so a radiometer that's measuring both the total reflectance from the Earth to get the total shortwave albedo, and then you have a long wave channel, and you have 3 views because you can't really measure a flux from space, but you get a much better idea if you measure the radiance at 3 different angles. And the idea is to put this all together, and it's kind of like and then that gives you the ability to do kind of an online closure experiment. So the LiDAR and radar give you the best vertical profiles of, let's say, the cloud and aerosol properties along the nadir. Do I need to review the idea of radiative balance in the atmosphere? Probably.
No, that's fine.
Okay. Cloud feedback question, we went all through that. That hasn't changed too much in the last decade. Because EarthCare does have an increasing role in providing data that will be directly used for weather forecasting. That wasn't within the original mission mandate, but it's becoming quite exciting. So that's the geometry of the mission. So like I said, you have the LiDAR and radar pointing down. The CPR, the Cloud Profiling Radar, is an instrument provided by JAXA, so that's not a European instrument. It's provided by the Japanese Space Agency, and it's actually built, though, by another Japanese agency, their National Institute of Communication Technology. And it's pointing straight down. And well, I'm giving nothing away, but there was post-launch, there was a lot of concern about how good the pointing is. That especially for the radar, if it's off a bit, that really screws up the Doppler. But it looks like we're hitting the ground within much quarter of a beam width. So in the order of like, if we predict the beam sensor's not there, we're like 20 meters off. So it's really solid. And after the pointing is spot on. The ironic thing is, so for the CPR, the Japanese had, until they refined it, had a model for where the antenna, which is quite big, should be pointing because of thermoelastic deformations along the orbit. But the model was actually amplifying everything.
Oh.
So at first it looked like the thing was swinging wildly, but when we turned the model off, so the knowledge of the pointing was bad, and when we assessed what the real pointing was, it was right on. So they do a better job just switching the model off. Of course, we had to compare EarthCare with the A-frame, the combination CloudSat and Calypso. So they were both launched in 2006 and were groundbreaking, and they lasted a whole lot longer than anyone would have guessed. Just to remind everyone why it's a good idea to combine LiDARs and radars, especially for cloud measurements, is that it's what the instrument sees is all it's all relative to the size of the wavelength you're using and the size of the scatterers. So for a radar, you see something like the square mass distribution. If and a mass is proportional to the diameter, the cube of the diameter, that's where you get the reflectivity, and that leads to the reflectivity being the sixth, proportional to the sixth power of the diameter of the droplets. So that means you see big particles, precipitation droplets, and ice crystals in the atmosphere with the radar are very good for that. Anything small like an aerosol or even non-Driscoll stratocumulus, not so good. The Lidar, on the other hand, sees something like the area, so d cubed, d squared. So that means you're very good at aerosols, molecules in the atmosphere itself. And because the interaction is so strong, though, attenuation is a big thing. So to put these together, and this is an example with CloudSat and Calypso, where you see that they're all looking at the same bit of atmosphere, but if you look at the CloudSat image, you notice you penetrate much deeper into the clouds, but you miss a lot of the thinner structure above, and the LiDAR is picking that out quite well. So by putting both of them together, you get a much better picture of where the clouds are and their properties. And in the area where you have overlap, you can do things like retrieve the particle size. And there's even more advanced methods that bring into things like the brightness, temperature, and reflectivity above to fill in a lot of details in the vertical profile that you would not otherwise be able to handle. And this is all explained in a lot of detail in one of the papers of the EarthCare special issue, which I'll talk about later. And I'll just now I'll just focus a little bit on APLID and then probably wrap up this part. So I mentioned that APLID is a high spectral resolution LiDAR. So what does that mean exactly, and what advantages does that give you? Well, a high spectral resolution LiDAR, in that case, unlike a normal backscatter LiDAR, you're looking at very small spectral bandwidths, and the advantage of that is that you can begin to tell what you have scattered off of. The problem with a backscatter LiDAR is, of course, you only have one signal, really. And you do not know, per se, if that's photon that you're receiving, if that's scattered off the background atmosphere, if that's scattered off an aerosol or a cloud particle. And if you see an attenuation in the signal, your signal, let's say, starts at a baseline and then goes up and then fades away, you don't know if that fading away is due to the fact that there's less cloud or aerosol there, or your signal is being attenuated. And you can do retrieval methods like the PLET method, but then you have to assume what the extinction to backscatter ratio is. With an HSR LiDAR, you can do something different. Like in a Raman LiDAR, with an HSR LiDAR, you can, if your instrument passband is like this, and this is your laser frequency, the spectrum from the atmosphere looks sort of like this. So this broad feature there, that's the scattering from the molecules themselves. The neural peak is from the laser itself. And you split this in a filter, so one channel gets more of the particulate scattering and less of the molecular scattering, and the other channel the opposite. That enables you to decompose the signal into components that are scattered from the molecules themselves or the particles. And the advantage of doing that is that if let's say your air density profile looks like this and you're looking like above, in the me channel, or this is the particulate channel, you will see nothing until you hit the cloud, and then you see something. In the Rayleigh channel, it'll follow the molecular atmosphere above, and then when you enter the scattering layer, you don't see any enhancement of the signal. you only see the signal fall off, so you get a direct measure of the attenuation. And that enables you to separately measure the backscatter and the extinction. And you divide the two, you get the extinction to backscatter ratio. And for aerosols, why that's a big thing is that nature cooperates to a certain degree. If you're interested in what these aerosols are, then you are able to take two measurements. Instead of assuming the Lidar ratio, you can now derive it. And you can also measure the depolarization ratio. I forgot to mention that Athlid is polarization sensitive, unlike ALS. And then this allows you to a certain degree, classify what these aerosols are. Now, for people that are interested in doing the simulation of the data for aerosol purposes, you would not necessarily need this knowledge, need this classification, because you probably should be then assimilating the level 1 signals themselves. However, you should also have in your simulation system the freedom to assign the Lidar ratio depending on the microphysical properties of the aerosols that you have. So, but we're still, so we would not, you may not be using the aerosol piping because that's crude, but you should be predicting what the Lidar ratio is to do in the simulation system. So, but then you really have then two almost independent pieces of information that should help, that would help really improve the sources, depending on the speciation. And of course, it's a growing area of importance. Well, I don't have to tell you about direct effects of aerosols around here. You're often subject to quite big plumes of Saharan dust, which I'm sure are affecting the short-term weather and the longer-term climate. And then you have the broadband radiometer, which I won't say too much about. But it's also quite a nice instrument, and it's actually it does deliver images too at the 10 kilometer scale. Mm-hmm. So you'd actually get images of the fluxes at the top of the atmosphere.
And the point here,
we don't have too many products that use that directly, but I'm sure they will be coming. So that could be something that's the use of this high resolution total wave measurements, I'm sure will be enhanced in the future. No, it's 1 by 1 kilometer or something. Yeah. So you have. So the images that have already been released look quite nice. There's something like 47 products in about 30 or 20 some processors, all organized into different chains. Of course, we have the level 1, and then we have the level 2A, so we have a number of single 2 products, and then the level 2B, which combine either multiple single instrument products, both in the level 1 and level 2. But if you simplify that even further, this gets back to the idea that I talked about earlier of the online closure, in which you have all of the you have each instrument first doing its own retrievals of what they can without cooperation with the other instruments. Then at the level 2B, you get the fusion of the different instruments to give you, and that's synthesized into these scene reconstructions in which you have an estimate of the 3D properties of the atmosphere. Then we're applying actually both a combination of 1 and even 3D radiative transfer calculations. It takes a lot of CPU calculations, but we're doing that, and then we have the online closure assessment. And it's early days now, and not all the products have been validated by any means, but at least on the technical level, the code has all been demonstrated that it's running in the operational processors. So this assessment, even now in the commissioning phase, is happening. There's many bugs. We're not within our goals yet, but it fundamentally looks like it's going to work. Of course, there's hundreds of bugs and things we still have to track down, but even not too many years ago, there was a lot of skepticism that we would ever get this running. And it's only because we had literally decades to prepare for this that we were able to do a lot of okay, just no, I don't have. That we were able to do a lot of simulations, and we had developed through the years a number of scenes, but the ones we developed officially for the algorithm development and ground segment testing were based on high resolution cloud resolving forecast models. And one of our scenes is a so-called Halifax scene. So there's a number of high resolution cloud modeling scenes all stitched together in an orbit that goes over Halifax in the province of Nova Scotia in Canada. So within a couple of 100 kilometers from my hometown. So these scenes were used as a basis, and on top of this, we had aerosol fields from the MAC project to be able to transfer things like this is the model extinction along the Lidar track of that scene, extracted from there, and from that to use this as a basis for modeling, in this case, what Atlas would see. And this is starting over Greenland, and you can see the LiDAR is picking up these ice clouds here. It's missing this very weak feature there. It's also important to know what you see, but also what you won't see, what you could be missing. A lot of super cold water here. You're getting a storm above the near Nova Scotia, and you can just see you're seeing the cloud tops here, more super cold water there. And out here in the Caribbean, you're seeing two aerosol layers. So down here, it's mainly marine sea salt mixed in with some cumulus clouds. And above here, you have some more continental pollution coming off the eastern seaboard of the US. And we can then apply our retrieval algorithms, which I'll talk about in detail in the next, I think it's the next presentation, to retrieve things like the LiDAR ratio. Instead of having to assume it, we can retrieve it. And in this case here, you see a clear contrast between the sea salt below and the so-called continental pollution above. And this is what the truth would be. You can see it's not, we can't follow things perfectly, of course. But one of the challenges is to you only have a limited sensitivity, and the signal to noise ratio of any space-based LiDAR is always going to be less than a ground-based one, because you're at least 400 kilometers away, and the receiver of Atlas is only a telescope like that. So, but it's impressive what it gets. And at the end of the day, we can, in terms of the classification, we can do what we considered to be a fair job of separating different aerosol types, but also separating the ice and liquid phases. And of course, this is the beginning of the chain, because this is then combined with the multispectral imager information and the cloud information and the radar information to get really even more sophisticated and better classifications and better cloud and aerosol properties. So the data usage, there'll be a lot of this data will be used in evaluation of parameterizations and process studies coupled with models to see if the models can actually replicate what is being seen by the actual observations. There is this crucial one here, and this has only increased in strength in the last few years, is that a lot of the products will be operationally simulated on a trial basis by the ECMWF. Not only the cloud profiles, but also from the aerosol side of things too. We're hoping for, and already some of the preliminary results are quite encouraging. So,
True, true.
and it's nice too with the SMWF with the weather centers that are simulating the products also are able to give a feedback into things like the accuracy, the calibration. Because if they first have to monitor the quality of the data before they know it's a certain quality, before they can use it in their models. And in this procedure, they're very good at detecting when there's, let's say, step jumps where something is wrong in the data. If the calibration, the sensitivity of a component changes, that will be that.
Relationship.
Yes.
Relationship.
So that's another important part of the quality model. And I'll wrap up there. So I hope people felt that was a little bit worthwhile for some of this people. I'm sure some of the audience, this was nothing new, but for others, I think it might help set the stage before I go into some of the. And I'll